Today we want to review for exam 2 and finish a few homework problems. Because a few of those we didn't get a whole lot of time for. And the homework's coming up due, right? So I wanted to point out there's a few problems we didn't get to discuss, such as this one. Right? And here's a note. When your variable x is in an exponent equation, how do you solve for x? This isn't a cure-all. I'll say, so to solve for x, try the following. Often this works. It depends on how complicated the question is. You can make a complicated enough equation, nobody can solve it. But you can try this. One, you isolate the exponential by algebra, right? By elementary algebra. Meaning put it on one side of equals by itself. Isolate the exponential function that has x in it. And then take the logarithm of both sides. Use your property that log of x to the k is k log x to get the exponent down. Now that it's out of the exponent, solve by your old techniques, old algebra techniques. I want to illustrate it with this problem number 3, I guess. No, it's not 3. This problem of the homework questions. I want you to be able to do these for the test. This is, suppose I have 4.98 population, or maybe I'm doing a radioactive decay problem and I get an exponential decay that says 4.98 to the minus x equals 10.4. And I'll round this to so many decimal places. Solve to 4 decimal places. I have to round. How do I solve that? I'll try these 4 steps, right? I'll isolate the exponential. We were doing a little bit of this last time, but we said there's more to come, right? This is the more. If you have an easy base, like log, like this is 2 to the minus x, then you can take log base 2 of both sides and get it out. That's what we did before. But if it's not an easy base, what you do is you just take the log of both sides and say, if these are equal, then their logarithms are equal. This is step 1. Oh, I'm sorry. Step 1 is to isolate. We'll say step 1 is it's already isolated, right? The exponential with x in it is already isolated. Now, step 2, we want to take the logarithm of both sides and say if they're equal, then their logarithms are equal. So log of 4.9 to the minus x is log of 10.4. So isolate the exponential, take the logarithm of both sides. Now the problem, we have the property that says log of x to the k is k log x. You can bring down the power and multiply the logarithm. So this equivalently is minus x times the logarithm of 4.98 equals the logarithm of 10.4. See how to divide that, how to solve that? I just gave away the answer. This is just a number multiplying minus x. I can think of this whole thing as minus the logarithm multiplying x. So I'll divide by minus the logarithm and have x. So this was step 3, bring the exponent down. Log of, we're thinking of this as x to the k is k log x. So you bring the exponent down out front by property 3 here. And now you divide by minus the log of 4.98, and you get x equals the right side log of 10.4 divided by minus, I'll put it out here, the log of 4.98. There it is. There's the answer. And your boss won't like this, right? Well, how many feet is it? You have to compute the logarithms, right? So you get your calculator out and it has the log button on it. This means logarithm base 10. Remember, every logarithm has a base. If you don't write it, 10 is the sum. Just like when you write a root, you don't put the index for the root. 2 is assumed. Second, the square root. So I'll take minus log 0.4, and I have to close my parentheses on here, divided by log 4. And I come out with negative 1.458678, blah, blah, blah. It gives me lots of digits. Remember how to round to 4 decimal places? 4 decimal places means 4 places right at the decimal point. So I count not this one, but from right at the decimal point. It's not significant digits, that's different. This is decimal places. 1, 2, 3, 4. I'm going to round it here. So I look at the next digit. If that's 5 or greater, I round this last one up. So I'm going to call this approximately, you don't have to use squiggly equals here, minus 1.4587 to 4 decimal places. All right. That's how you solve one of those. If x is in an exponent, you take the logarithm of both, you isolate the exponential, take the log of both sides. That gives you an equation you can solve with algebra by pulling the exponent down. I'm going to do at least one more of those because I want to ask at least one of these. Sometimes instead of solving for a specific number, you're solving a formula, right? So you get a problem. Like one of these. Down here where the little hand is going around. Let me put it on for the people online. What's different over here? This one. Solve the formula for the specified variable. A equals B times quantity 10 to the KT minus 1 for T. What is T equal to? This time I won't get T equals a number because it's variable. I can't solve it. I can't get a specific number. I still solve the equation. And if I have this formula for A as a function of T and this other variable B, I can turn around and solve it for T as a function of A and B using logarithms. So here's the other example then. A equals B 10 to the KT minus 1. And the problem is solve for T. This is the trouble on the test. You'll see this and go, oh, because you've been doing linear equations and power equations, and you have to recognize when T, the variable, is in the exponent, you isolate the exponential and take the logarithm on both sides. That's what I'm saying about memorize the method. Don't just do them all the same and then not be able to start it on the test, right? When you see T in the exponent, isolate the exponential, take the logarithm of both sides. That's the trick. And I put 4 steps, but you can really just think of those 2. Right? Anything more than a 3-step method is different. Except alcoholics recovering and so forth. Anyway, we can do 1, 2, and 3, right? So what do we do to do this? Step 1, we isolate the exponential that contains T. That's step 1. So I'll do that by dividing by B and get A over B. Left side divided by B is the right side divided by B. T to the 10 to the KT minus 1, right? Now I'll add the 1 over and get A over B plus 1 equivalently, right? I can add one of these time equations, equivalent equations, got the same solution set, right? 10 to the KT. That's what we mean by equivalent equations. They have the same solution set. The double arrows, remember, mean equivalent. So this has the same solution set as this one, has the same solution set as this one, assuming B isn't 0. We're assuming that in equation. Otherwise, I just say A equals 0. That can't be right? Something different than that. So assuming B isn't 0, these are equivalent. And then this is equivalent by adding 1 to each side. You know I do that. Now I've got the exponential isolated, right? So what do? Take the logarithm of both sides, right? Log of the left equals log of the right. There it is. Property 3, I don't usually even say this step, but is to bring the exponent down, right? The idea is once you do that, you recognize what to do. It's 10 to the KT. If I think of this as log of x to the k is k log x, the exponent comes down. So step 3, bring the exponent down. To multiply. That's our property of logarithms. That always works. The left stays the same. Log of a over b plus 1 equals kt times the log of 10. Well, we're lucky in this case. What's log base 10 of 10?
1.
Yeah, 1, right? Log base b of b is equal to 1 always. So this is going to be easier than usual. Even if this wasn't 10, though, we could just divide through by this logarithm and we'll still get the answer. But on this one, to get the simplified answer in the back, it's a little trickier. You have to have 1 here, right? Because they won't want you to put log 10 on there, I think. Now we'll divide it by k and we'll switch sides and we've got t equals 1 over k log, in fact, let's write it this way, log of a over b plus 1. I think this is the way the answer was expressed. Over k. So let's just divide both sides by k, getting rid of the 1. And there's what you have now, a formula for t expressed in terms of a and b. So there's the power of these logarithms. They can get things out of exponents. They can solve exponential equations, we say. That's the last thing I want to do. I hope that'll help you to finish the homework that's coming up due. Any questions on those? We can do some more of those for class 2, but see any of those up there you want to do the others? People working on them already. Yeah.
Right there with that 1, it just automatically cancels out right there.
Yeah, if you have
Okay.
the idea is I have x times 1, I just write x because it's the same. If here I've got 1 times kt, I just 1 times anything is just question of it. I just didn't write the intermediate step. This is equal to kt because the times 1 is going away, and then I'll divide by k. Other comments? Okay, well, let's, you got the review problems, maybe you're looking at some of them I asked you to last time. And there can be anything similar to the homework, I'll be able to solve these kind of problems we just did. I think there's too. What would you like to look at? Anything in particular? We've got all those things from chapter 3 also at the beginning. Yeah.
We do 8.
8, okay. Probably picked the hardest one. That's probably good, is what we need to do. All right, so here's an interesting problem, 8 off the review. A rough estimate for the radius of the nucleus of the atom. We looked at this before. A rough estimate. This is a hard problem, right? A rough estimate for the radius R of an atom in a nucleus. Nucleus of an atom, I'm sorry, or atomic nucleus. Okay. Atomic nucleus is R equals K A to the 1/2, right? Where A is the mass number and K is 1.3 times 10 to the minus 13. For this problem, we're gonna say, suppose A is the mass number of iodine, 127, which, that's its mass number, 107, protons and neutrons in the nucleus. So A is 127, and then the K, you're told, well, K always is 1.3 times 10 to the minus 13th. Let's just put that part in. A, for a specific atom that has mass number 127, that's iodine. 7. Estimate R. All right, so this one is just telling you to plug in the numbers and see what you get. All right, so I'll compute R equals K is 1.3 times 10 to the minus 13th. This challenges you to use scientific notation in your calculator, because suppose you try to enter this without scientific notation. Your calculator maybe carries about 10 decimal places, right? And so you put 0.000001, and you get to the 10th one, and you can't get to 1.3 in the 13th and 14th places. So you have to enter this in scientific notation. That's that E or EE button, depending on the calculator, 1 or 2 E's. R equals K times A to the 1/2 means square root of A, which is 127. So that's what you do. You just put in this number for K. For square root of A, you put square root of 127. So I'll put that on the calculator. I'll put 1.3, and it's E or E. I'm not sure on this one. EE above the comma. So I'll push the second key, because above the comma on my TI-84 it says EE. And then I'll push this key for the negative number, not the subtract key, minus 1, 3. So these are all keystrokes also. I just get tired of writing boxes. That's 1.3 times 10 to the minus 13. And then times square root, again, is above the square, so we have to push second x squared on this calculator to get the square root. Your calculator may not have a square root. You might have to push the caret 1/2, or caret 0.5, or caret 1/2. Square root of 127. Many of these calculators, you need to close the parentheses here because it doesn't close them automatically, and then you need to push enter. Okay. Okay, when I do that, 1.3 square root 7, close. I got 1.4 times 10 to the minus 12. It says 1.4 E minus 12, meaning 1.4 times 10 scientific notation. And I think this is in, I didn't write the units down at the time, it's in centimeters. cm for hundredths of a meter, centimeter. So put that in here, centimeter. Well, it's actually times 10 to the minus 14th meters, if you're familiar. All right, so that's part A. If the nucleus is roughly spherical, what is its volume? On the test, if I give you this question, I'll give you this additional hint, because I don't want you to have to memorize the volume of a sphere. Okay, so put it on the practice set. So B, what the volume of the nucleus, if it's spherical. There's a formula for it. It's in the text. And its volume equals 4/3 pi r cubed. What a crazy formula, huh? Wasn't it easier with an area of a circle, which is pi r squared? 4/3 pi r cubed for the volume of a sphere. Three-dimensional analogy to circle in the plane, right? You wonder how to get this crazy formula. You can take calculus. It's calculus 3. You can actually prove that after a year and a half of wading through it. There's actually a very famous problem where Archimedes, one of the 3 greatest mathematicians of all time, he was able to prove, I think this is the result exactly, that if you take a cylinder and inscribe a sphere inside it, the sphere actually takes up exactly 2/3 of the volume of the cylinder. I think it's got 2/3 of the surface area too, or something like that. And so he had this really neat result. Long, like 1600, I think more than about 1800 years, something like that, before calculus came along. He was able to come up with this thing still without calculus. So it is possible to do it with exhaustive methods. But he was so proud that he had to put it in his tombstone, it said. So anyway, there's neat problems with antiquity with spheres. Important to the ancient. All right, this is 4/3 pi r cubed, so we just have to calculate on the calculator 4/3 pi times 1.4 times 10 to the minus 12 cubed. And we can put that in the calculator again. Take 4 divided by 3 times, do I need to put parentheses? Oh, yeah, because it does these left multiplications and divisions left to right in order. So we'll do the division first and then the multiplication. And it wouldn't matter anyway. I could do the multiplication first and the division. It's the same number. So I don't need parentheses here. And then times r. What's nice is if you have this already sitting on your screen and you don't want to flub it up, right? You push second and this little minus key. It has, I think that's the one. Hands. I used to hand these out in class, these calculators. I just can't. Second hands, to get this gets the last number on the display. So if you've already got this one up, 1.4 times 10 to the minus 12. Not 1.4, rounds to 1.5. Let's call it 8.465 times 10 to the minus 12. 5. There's more digits here. I should have copied more down. All right. So times second answer, and then to take a third power, you can push caret 3. Enter. Do I need parentheses now? I actually don't, because what will happen if you think about it, it will do powers before the divisions and quotients, right? It does parentheses first, they're the strongest. Then it does multiplications and divisions left to right on an equal basis. Then added, I forgot powers. Powers next, then multiplication, division, then addition, subtractions left to right last, on an equal level left to right. Unless you buy, I've seen a couple $2 calculators that don't work this way, but only really like dollar store import kind of things. So when you look at this, what it will do is the power first, it will take the last number to the third. It will divide 4 by 3. That's good. And multiply by pi, multiply that result. Multiply that result times this one. So you don't need any parentheses in this. It'll work perfect. It will do the power first, just like you want, and it will do the division multiplication in order that works. So let's try that and see if I can get the right answer. I can. So it's off like 4 divided by 3 times, and to get pi, remember you push second caret. Did I forget my pi? No, there it is. I forgot my pi, didn't I? It's 4/3 times second caret gives me the pi times second answer to the third. I forgot my pi in here. So this goes in between. 4/3 times pi from these times last answer cubed. 4/3 times pi last answer. And I got 1.3517 10 to the minus 35. So let's say EE minus 35 on the calculator. I should write those down so. Post them. And now this is the volume, so what are the units on this one? Cubic centimeters, right? It's length times width times height is the volume. So it's centimeters times centimeters times centimeters, cubic centimeters, right? There's that one. Now the last part of number 8. If the density of the nucleus is measured in mass per unit volume, what is the mass of the nucleus? Oh, let's see, I'm sorry. Yeah, okay, yeah, should have said, what is the density of the nucleus? This was. I'm gonna have to drop off C, there's a typo in there. So omit C on part A. I'll just drop that off. It was just a multiply. When I copied and pasted this actually out of the homework set, some of those paste things don't come in. So omit part C on there, I'll just drop. C. Well, what you do is you can take this volume and multiply it by the density to get the mass, is what you can do. So if I told you what the density, average density of things. Not what I want to emphasize, so I'll drop it rather than. Questions on that one? Good question. Okay. What else is difficult? Anything in particular? Which? Okay, the whole thing?
Mostly just like the setting up of the decay formula.
If we're being nuclear physicists today. Plutonium 238 here. 238 is a radioactive element that decays over time into a less harmful element, one that doesn't have radiation, at a rate of 0.8% per year. T. A power plant has 50 pounds of plutonium to dispose of. So we'll say if there is 50 pounds plutonium it's another one I copied out of here. No, it's copied right this time, but I don't like the. Check out something on that still. We'll leave it as it is. Write a function that describes the exponential decay. What function describes, this is the application, the decay. Remember that radioactive decay is without other interfering factors, exponential. It's an exponential model. The reason is that if you have a certain amount of plutonium, it has a certain half-life, they call it, where over that period of time, it decays to half of that amount. Over the same period of time, it decays to half that amount again, then half amount again. And because it keeps doing this, it's an exponential decay. That's property of exponential. It decreases by the same percent each period. This one decreases by 0.8% each year, for instance. And so I don't know how many years it is for a half-life when it gets down to 50%. You get the idea. If it decreases by a constant percentage, it's an exponential decay model. What happens, however, in practice is there are other things in the atmosphere that screw it up sometimes. Like when they put out the first nuclear bomb, nuclear test back in the late 40s and so forth. The radiation they put up in the atmosphere changed, like dating of some of these metals and so forth. Steel made before that time has very little effects of radiation, and the steel made after that time has effects of radiation in it. The difference, you can tell steel made before. The nuclear testing started after, and so there are things like that, and it depends critically on the atmosphere. As we change our atmosphere, a different amount of radiation will get through and so forth too. Radiation coming from space, that kind of radiation that causes, for instance, radioactive carbon in the atmosphere, just for certain elements of them. But anyway, there are environmental factors that affect these things by people or by radiation from space that changes in the atmosphere and so forth. But barring those kinds of interference, this thing naturally decays exponentially. So what do I write for the exponential model? You just memorize this, that the amount of element left is the amount at times zero. I like to write A0. I can't remember what the book used. Was it A0 or P0? It seems like it's something else.
This P0.
P0? Okay, P0 is the initial amount. Times. So let's write it this way. 1 plus R to the T. I think this is the one they use for this model. If you have a so let's write it like that. So this is the exponential decay model given an initial amount. And the decay factor, 1 plus R, is just 1 plus the rate of decay. Actually, R is the growth rate, not the decay rate. So for a decay, we're going to have to make it negative. Well, this is actually equal to P0, the initial amount, 50 pounds, times 1 plus minus 0.008. You have to write the percent as a decimal. So the percent means times 1/100. So you move it over 2 places, you get 0.00. 0.8% is 0.008, right? To the T. And so this is what the exponential decay will look like. It's 50 times 0.992 when you do the subtraction to the T. There's your exponential decay model. A equals P0, B to the T. Yeah, okay. And with B less than 1, it'll be decay. That's part A.
Just for B, you plug in the 10. T.
Yeah, I think that's, I'll take a look, but I think that's right. Yeah, B, how many pounds will it be after 10 years? So that's B at T equals 10 years. You just plug that into the model. Get the amount is 50 times 0.992 to the 10th. And on the calculator, it's 50 times 0.9 caret for power 10. Enter to evaluate it. not so bad, all right, 46.1. After 10 years, it's still mostly all there, 46.1. This is why you wanna get rid of that, not build up too much radioactive decay, because they're around a long time, right, 100 years later, so, you know, some left. 46.1. Okay. Here's something I definitely want to ask you also. You have to be able to do these exponent properties. They are absolutely critical in all your later courses. You want to be good at them. Here's number 12. If I take a to the minus 12p times a to the 3p, I say simplify this. What do I get? You want to use your property that says a to the b times a to the c, the exponents add a to the b plus c, right? So you add those exponents. This is a to the minus 12p plus 3p is a to the minus 9p. If I take part b and I say, what is a to the p over 2 times a to the p over 3, what's that? A to the sum of those exponents, p over 2 plus p over 3. Now, how do I reduce that? I really want to simplify it or it's a point off, right? What you can do, this is a to the p times and factor out the p, 1/2 plus 1/3. P times a half is the first one, p times a third is the second one. And now what's a half plus a third? You can do it on the side. Right, you have to put these over a common denominator to add quotients. You can't add them till you do that. So multiply this one top and bottom by 3, right? The denominator of 2, I get 3/6. This one top and bottom by 2, the denominator of this one, get 2/6. Add the numerators over the common denominator, and you get 5/6, right? That's how you add fractions. So this is a to the 5/6 p. We usually prefer to put the number before the variable. So there's how that one simplifies, a to the 5/6 p. C, suppose I gave you a to the, read that. What is this, 2p over a, what's that one?
P minus.
This 2p minus 1, yeah, right? This is a to the 2p over a to the 1, right? A to the 1 is a. And now, when you have a quotient, we have this rule that a to the b over a to the c, the exponent subtract is a to the b minus c. So I'll subtract these. This is a to the 2p less 1. What is a to the 1 over r to the p? And then the question comes in, does that mean a to the 1 over r and then to the p? Or does that mean a to the 1 over r, 1 over r taken to the p? Which one does that mean?
It says A 1 over P.
Oh,
It's not
P,
ours.
I'm sorry. 1 over p. The answer is this. It's just a matter of notation. When we write this means a to the power of b to the c. That's what it means. If we wanted a to the b to the c, we would have used the property that says you can a to the b to the c is a to the b times c, and we would have written it as a multiplier. We don't write. If we write this, we mean this one, because this one we would have reduced to this one. Right? So that's what it means is the latter here. This means a to the 1 over p power. How about that? Like that. That's what it means. Definition, if you like. Just a matter of choosing notation. And now how about that? Well, this is A to the 1 to the P over P to the P, right? If you take power of the top over power of the bottom, we have this property here. Maybe I better some of this. I need some of the exponent. Now I'm using the property A over B to the C, P to the C over B to the C, right? So I'll take 1 to the P over P to the P using this property. So I write that as A to the 1 over P to the P. And that's about as simply as I want to write it, like that. You can also, if you prefer, as the P to the P root, okay? That'll be acceptable. That's the other notation for that. Notation means first power and P to the P. I took this from the book. This is what this means, so I'll go with that. Now here's number 20. I thought this was a hard problem, so I want to make sure I did this one. Suppose I said A solve this equation, 4 to the x squared equals 9. I wonder what the solution x is for that. How can I solve that? We did this today, actually. If x is in an exponent, what do I do?
Isolate.
Yeah, isolate it. It's already isolated in this case. Right, the exponential with x in it is already on one side by itself. So then I take the logarithm of each side. So I'll take log of the left equals log of the right. And again, when you see 4 to the x squared, it means imply parentheses up here, not down here. You would have and then once you've done that, you can pull the exponent down. So I write this as x to the k, log of x to the k is k log x, except now x is up here. So pull the exponent down, you get x squared times log of 4 equals log of 9. And now log of 4 is just a number, right? This is like, if this is 2 times x squared, you divide by 2. When it's log 4 times x squared, you divide by log 4, right? And you write x squared equals log of 9 divided by the log of 4, right? And if x squared is this number, then what's x? This is how you solve an x squared equation. You isolate the x squared and take the square root of both sides, I should point out. So this was step 3 to bring the exponent down. Step 4 is the algebra. You have an equation involving x squared. You solve it by isolating x squared, old method, and take the square root of both sides, plus or minus, because when you have x squared equal a number, x can be plus or minus the square root of that number, right? There's positive and a negative. This notation means the non-negative number whose square is 4, so it's 2. And there's 2 answers, plus or minus 2. Same thing here. If x squared is this number, x should be plus or minus the square root. Hope I don't emphasize that too many times, but it's such a common mistake. I feel obligated to do it a lot of times. So x must be plus or minus, and there's 2 solutions: square root of log 9 over log 4. Let's see what that comes out to be. This is a calculator problem. Said round to 4 decimal places, right? So square root is second log 9 close parentheses divided by log 4 close parentheses. Make sure you close the parentheses on the logarithm. The calculator put in a parenthesis like that. You have to close this one, or guess what will happen? The TI-84 will close everything again. You'll take log of 9 divided by log 4 like that. it will close everything at the end. You have to close your parentheses here. It'll leave it open and close everything at the end and give you the answer. In fact, it'll put it outside the square root. So I'll close the parenthesis on the log 9, close the parenthesis on the log 4, and then close the parenthesis on the square root, just to be careful, right? And I get plus or minus 1.2589529, blah, blah, blah. I said round to 4 decimal places, plus or minus 1.25895. This next, the 5th digit after the decimal place is 5 or greater, so I have to round this up to 90. And you keep the 0, why? Everybody assumes you only round it, if you drop it, they assume you round it 3 decimal places, right? So the 0 is a placeholder showing that this has 4 decimal place accuracy. You have to write the 0 in rounded numbers. So that's a significant digit, a rounded digit, right? So, yeah.
Oh,
All right, and then there's part B. So suppose I want to solve this one. 2,000 equals 13, that dot is times 7 to the minus 0.5x. How do I solve that?
Isolate the.
Now, this again is what we did at the beginning. We'll isolate the exponential. This time it's not isolated. So I'll divide both sides by 13 and get 2,000 over 13 equals 7 to the minus 0.5x. Now the exponential is all by itself on one side of equals. So I'll take the logarithm, not on both sides. Log of 2,000 over 13 equals log of 7 to the minus 0.5x. The purpose of taking that log is to get the exponent out. So I now bring this step 2, the exponent down by the properties of logarithms. And write it as minus 0.5x times log of 7. Then finally, I use my old method to solve for it. It's actually very easy at this step. This is like the monster under the bed. It looks real scary, right? That looks scary, but there's not really anything there. Let's try this. Log 7 is just a number, right? If this was minus 0.5 times 3 times x, you just divide by minus 0.5 and 3, right? So you just divide by this number and divide by minus 0.5, and you got x equals log of 2013 divided by minus 0.5 and divided by log of 7. Right? So that's the answer. You can make it look a little neater, but you don't need to. You just need to run it in the calculator and see what you get, right? The log of 2,000 divided by 13. Make sure you close the parentheses here. It'll close after the divide otherwise. Divided by 0.5 log of 7. I get x equals minus 5.1759 when I round to 4 decimal places. Now, this one you have to be careful in your calculator, actually. There's 2 numbers in the bottom. If I type log 2,000, I won't write all the boxes this time, divided by 13, divided by minus 0.5 times log 7. I'm going to get a really wrong answer. Why? But I'll put in some more parentheses. Because it will close the parentheses on the logs right at the end. If you don't put parentheses in, it will take log of this whole thing here, right? So you have to close your parenthesis in the logarithm. The calculator will automatically insert a parenthesis here. So I have to close it with a parenthesis here. Log of this number, right? So put in your thing to close the logarithm. Same thing here, the calculator put a parenthesis here. Now if you leave this one off, it doesn't matter because it will close at the end. That's where it goes anyway. But it's best to put them all in. Sometimes you forget to put one in here, then puts in here and messes it all up. If you put them all in, then you find out when you've missed one up here, right? And now there's still something wrong. What is wrong? It does divisions and multiplications left to right on an equal level. So it will do this division and then multiply the result. It will do this one times log 7 up here as I typed it in, right? Because I didn't put parentheses. In order to divide by log 7, I need to put parentheses around here. So this one divided by the whole product, right? Otherwise it will divide by this one and multiply by this one on top. So do that, put these parentheses, or you can just divide by one and divide by the other, that works too. Harder to divide, but it works. Right? So be careful with your calculator keys. You should get minus 5.1759 by like some of you got. Okay. There's some of the trickier problems. I'm going to ask you logarithms. Those are always tricky, and I want you to be good with them when you come out of this class. I'll tell you truthfully, though, logarithms, one of the difficulties in algebra is that you come out of the class and you don't use them for a while. Everybody forgets them all. I guess you just have to review them. It's normal to have a lot of these go away, start using them in some other class. So expect that, but I still want to practice them a bunch because they can be difficult. Here's number 9. The log of 9t plus twice the log of t minus the log of square root of t, we did just about like this in class, equals log of what? How can I write that as a single logarithm? In the blank. Remember these? Last time? Look at these at the end because these are kind of new. I think they're still harder. Here's what you can do. You can use your properties of logarithms backwards. All right. Log of t to the k is k log t. You can put the multiplier back up in the exponent. Rewrite this equivalently as log of 9t plus log of t to the second power. So you just do a reverse order, put the exponent back. This one, I should say, is equal to this one. This will be the question over here. So I do that, and now I remember the properties of logarithm. Log of one number plus log of another number is what? This is what makes logs hard. There's a bunch of properties, right? You want to have all these memorized for the test, right? Log of x plus log of y, any base, is what? Log of x1. Log of the product is the sum of the logarithms. We had a bunch of properties here, I'll remind you, but you want to know all these for the test. Log x minus log y is
Log x.
log of the quotient, log of x over y. And then this one we wrote earlier, log of x to the k is k log x. And then our basic properties, log base b of b is 1, log base b, any allowed base whatsoever of 1 is 0. Log base b of b to the x is just x. You can derive this one from the properties above. But we had all those properties of logarithms. You want to make sure you know all of them. Right? So memorize these. Put a big star here by the things you got to know all of them. And now I've used one of these. I put the exponent up. That was this one. Now we use the property that says if you have the sum of logarithms, you write them as a logarithm of product. This is log of 9t times t squared. And then I have the trailer here, log of square root t. Now what should I do next? I have a difference of logarithms. I use the property for log minus log is log of the quotient, right? So I'll say this is log of this one divided by this one. I'm thinking of this as x, this is y. Log of x minus log of y is log of x over y. Log of 9t times t squared over square root t. There it is, a single logarithm. And then I want to point something out. You can't do this the first time because it just gets too much to remember. But do you notice something about this? I could have done this all in one fell swoop. Well, from here to here. When I have sums and differences of logarithms, I can do it all at one time. It's just a logarithm where you multiply all the things that are where the logarithms are added and divide by all the things where the logarithm is subtracted. Right, so I take log of this times this divided by this. And that's, I can get here in one step instead of two. All right, so if I give you another thing, I say log A plus log B plus log C minus log D minus log E. What does that come out to? I just do it all in one fell swoop. It's log of, multiply all these, A, B, C, divide by these, D, E. I've seen do it all at once with these two properties here. That's what you can say on the second. So this will be a side note. Now, this is true, but I want this simplified. When you have t over square root t, you really want to write that as log 9 t over square root, right? T over square root t is square root t over square root. Cancel them, right? So it's just square root t. So t over square root t and right is square root t, and this is 9 square root t squared. And get rid of the denominator, always by this property. So this is a correct answer. However, you always put the square root last, so we call it 9 t squared square root t. That's an allowable answer. Another answer, sometimes this is a little messier. It's nicer to use the fractional exponents. Call this t to the 1/2, right? T squared times t to the 1/2, and then you can add the exponents, 2 plus a half. 9t to the 2 plus a half by using your property of adding exponents is log of 9t to the 5/2 or 2.5 if you prefer. I would prefer this. And so you put in here 9t to the 5/2, but I'll also accept this. This is when you don't want to write what we call rational exponents, fractions as exponents. And this is when you do want rational exponents. You can use either notation. Pretty good on that one. So know those properties of logarithms next time. We're going to use them some more during the semester. Here's some I want you to do with logarithms too. I'm emphasizing logarithms because I think they're harder, but please ask me all the other ones too. Here's 14a. What is the exact value of the log base 3 of 27 if I actually do exactly this one? You can do it on your calculator provided you learn how to do logarithm base 3. But you don't need a calculator for this. What is it? And even then you have to learn the trick, which we're still working on. What is this exactly? 3, yeah, right. How do you get that? The way you do these exactly is you can only do it if you can write this as a power of the base, right? If you write the argument as the power of the base, the log base 3, I'll write 27, wait a minute, is 3 cubed, right? Now log base b of b to the x is just x, so this is 3. Using the property log base b to the x, they undo each other. Log base b undoes that exponential base b and just gives you x back. So there's that one. Logarithm property there. Or you can pull the exponent down. Base 3 of 3 is do it too. So practice those and do some similar ones out of the homework. This one, B, what's log base 2 of 1/2? Have to be able to do this too. This is basic. What is it? I have to write this number as a power of 2. What power of 2 is it? Ah. Right? 1 over 2 to the 1 is 2 to the minus 1, right? It's a log of 2 to the minus 1 is a half. Oh, log base 2. Log base b of b to the x is x. There it is. It's just minus 1. How about that? Exactly. These logarithms base 2 are very important to computer scientists if you're in that category. What is the exact value of log of 10 to the minus 37? What's that? This one. The base isn't written, it's base 10, it's a common logarithm. Log base 10 of 10 to the minus 37 is minus 37, right? Log base b of b to the x, right? Here's D. What's the log base 3 of the cubed root of 9? Oh, what do I do with that? How do I write this as a power of 3? Yeah, exactly. Roots are just rewritable as fractional exponents, right? Third root, and this is 9 to the first power and third root, so you write it as 9 to the 1/3. Now I can pull the exponent down and say it's 1/3 log base 3 of 9. Oh, what good does that do me? Now I can write 9 as a power of 3. So this is 1/3 log base 3 of 3 squared. And 3 squared, right? Log base b of b to the x is just x. So this is 1/3 times 2. This whole thing just comes out to be exactly 2/3. Right? So tricky problems there, right?
Number 3.
Yeah. This is another one I absolutely expect you to agree with these formulas for powers. Those are formulas for logarithms. Those are formulas for powers, right? So 3A says this, if I were to rewrite sum of terms are just the things that are added together, so it just really means rewrite as a sum. Each of the form a number k times the variable x to a power p. Right, for some multiplier coefficient we call power. How about this one? A says 2x plus 4 over 6x squared squared. These are absolutely critical in calculus and all later courses you might take to be able to simplify these things. Formulas you use there depend on you simplifying these so you can use them. What can I do? Well, if I have a power of a product, what do I do with it? If I take a, b to the c, that's a to the c, b to the c, right? I just take each thing in the parentheses, that power. So the bottom is 6 squared times x squared, right? By this property. Now, all right, how about x squared squared? What's that? Yeah, a to the b to the c is a to the b times c. These multiply, so 2 times 2. So this is 2x plus 4, doing lots of steps here over x squared times x to the 2 times 2. It's 2x plus 4 over 6 squared, which I can write as 36, I guess. That's not because Yeah, let's write it as 36. So 36 x to the fourth. And now I want to write it as some of terms like this. So I'm going to multiply it out. Or break it up into two pieces. I'm going to write this as 2x over 36x to the fourth plus 4 over 36x to the fourth. This way I'll just have x, a power of x multiplying each term here. These are terms, things that are added. Now x over x to the fourth, what do I do with that? Maybe first I should say 2 over 36 is 1/18, right? Cancel 2's out of here. But a to the b over a to the c, recall, is a to the b minus c. So if you think of this as x to the 1 and x to the 4 is x to the 1 minus 4. There we go. 1 minus 4. Similarly over here, 4 over 36 is 1/9. And then I have x to the 4 on the bottom is x to the minus 4 on the top, right? And so this is x to the minus 3, if you like. I'll write this as 1/18 x to the minus 3 plus 1/9 x to the minus 4. That's what I'd like to see in the text, in the test. A number times x to the power plus a number times x to the power, sum of two terms, equivalent to the first thing. Right? But you often have to do this in these power models, is write it in this form. Let's see how long b is. Let's see. Yeah, let's just do b real quick because it's easy. Suppose I have x to the fifth over 5, x cubed over 5. This is an easier one, actually. Minus 2 over x squared. What do? I'll just think of this as 1/5 times x cubed. Why is that the same? I did it over there already. But the idea is if you wrote this as x cubed over 1, it'd be top times top over bottom times bottom. You'd recover this. So you just write it as 1/5 x cubed. And this one, x squared, 1 over x squared, you write as x to the minus 2. So write it as minus 2, x to the minus 2, right? With 1 over x squared. So that one I would write like this. All right, it's about time to go. Come see me if you have questions. I have an office hour at the end of the hall at 12:30 also.
Thank you.
Yeah, thank you.
Thank you, sir.